Whoa, 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 whoa. You know you love me, I know you care. Just shout whenever, and I'll be there.
Hello everyone, this is Mir Shabir. You are watching Vibrant Institute of Mathematics. Before starting our topic, let me tell you, please subscribe our channel Vibrant Institute of Mathematics. Press the bell icon for the latest updates. Now today's topic is on Cauchy's homogeneous linear differential equation with variable coefficients. We have done already one single lecture that was based on generalization of Cauchy's homogeneous linear differential equations. It is so simple idea. Here today's topic is on Cauchy's homogeneous linear differential equation, but we will take today a numerical session. First of all, I will give some recapitulation of this idea that will become the heart of the lecture. That talk will become the heart of the lecture. You imagine this is the Cauchy's homogeneous linear differential equation. This is a homogeneous linear differential equation. It contains variable coefficients. That's a Cauchy's homogeneous linear differential equation with variable coefficients. When I substituted, as per generalized lecture is concerned, we substituted in this very linear differential equation with variable coefficients. We substituted some elements inside this linear differential equation with variable coefficients. Cauchy's homogeneous linear differential equation with variable coefficients. It is transformed. It is transformed into a new concept, a new differential equation. That the resultant differential equation is a differential equation which contains constant coefficients. That is a linear differential equation with constant coefficients. At that time, Cauchy think my differential equation, that is a linear differential equation with variable coefficient, is converted into a new one. We want to solve this by substituting some elements. Those elements was this by taking transformation of this differential equation, so by putting the value of x is equal to e raised power of z, or z is equal to log of x, and using this operator d divided by d of z is equal to d. Using this operator d divided by d of z is equal to d, and then for some simplification, we get this x into dy by d of x is equal to d of y. When you see in numerical way, in numericals, when you see this dx into dy by d of x, you can use d of y. When you see x square into d2y by d of x square, you can use d into d minus 1 into y. Those are the elements. X cube into d cube y by d of x cube, you can use d into d minus 1 into d minus 2 into y. Memorize this idea. Memorize this idea. As per the numerical practice is concerned, when you can use the values of x into dy by d of x, x square into d2y by d of x square, x cube into d cube y by d of x cube. Those are the values used, just and so on. Those are the values used just substituted in this linear differential equation with variable coefficients. This is changed into a linear differential equation with constant coefficients, and the methods already discussed for linear differential equation with constant coefficients. Let us give the numerical way. Numerical way I can practice here. This is one of the example. This is x cube into d cube y by d of x cube plus 2x square d2y by d of x square plus 2y is equal to 10 times of x plus of 1 by x. This is a homogeneous linear differential equation with variable coefficients. Why so variable? Because in front of this there is x cube. In front of this there is x square, x cube. Those are the coefficients of this, but this x means a variable. So this is a linear differential equation with variable coefficients. So first we will use all such elements. So our first motive is that we will convert this linear differential equation, Cauchy's homogeneous linear differential equation, into a linear differential equation with constant coefficients. So we can use this idea first. This dx into dy by d of x, d2y by d of x square, and d cube y by d of x cube. As per the values of this value, this x into dy by d of x, x square into d2y by d of x square, x cube into d cube y by d of x square, we will use its right hand sides. So this is d of y, d into d minus 1 into y, d into d minus 1 into d minus 2 into y. We will substitute here. Let's take the solution here for this given differential equation, which is homogeneous differential equation. Cauchy is homogeneous. So this is the value here, x cube into d cube y by d of x. It is simple. So we will take this one right hand side here and paste here. So I can continue this one. This is here. We can write d into d minus 1 d minus of 2 into y, plus this is 2, this is as it is. As per the value of this is concerned, this x square into d to y by d of x square. So we will use this line, this one, this is d into d, and paste here d into d minus of 1 into y plus of 2y is as it is equal to 10 times of this one. This is x plus of 1 divided by x. And use the idea here, I can repeat this one, this is equal to 10 times. The value of x, I will transform, I will use the element x. Whenever you see x, you can use e raised power of z, this one. You can insert e raised power z here, as per the value of x is concerned. This is plus, this is 1 divided by, this is ex here, this you can use e raised power of x here, e raised power z here, sorry. This is e raised power of z. So I will repeat this idea. We will take y common throughout, this is y here. This will come to be equal to, this is d into d minus of 1, d minus of 2 plus times of, this is d into d minus of 1 plus of 2. This is y, this is equal to, this is 10 times of e raised power of z plus times of, I will take this quantity e raised power z into the numerator, it becomes e raised power minus of z. We will simplify this concept. This is d into d minus 1 into d minus 2 plus d into d minus 1 plus of 2. You just simplify this, take a piece of paper and write down this one and simplify this. This will come to be a cubic here, cubic factor here. This is of the form d cube, this is minus d square plus of 2 into y. When you simplify this one, this concept, it will come to be d cube minus of d square plus 2 into y is equal to 10 times of e raised power of z plus of e raised power of minus of z. So this is the differential equation. So this differential equation, you know that d cube contains a coefficient 1 here, d square contains coefficient minus 1 here. This is those d and d here contains a coefficients. So this is clearly transformed. This was a differential equation containing variable coefficients, but this is the resultant differential equation contains constant coefficients. So this is transformed. We can use the methods, you know that any kind of linear differential equation with constant coefficients contains a solution of the form y is equal to complementary function plus particular integral. That means you will calculate two components of the solution, given solution y. That is complementary function is the first component and second is particular integral. Let's calculate first of all, calculation, that is y is equal to complementary function only. Complementary function, first of all we will calculate complementary function. Now the rule is, the auxiliary equation is as, the auxiliary equation is this, putting this one equal to 0, this is d cube minus of d square plus of 2 equal to 0. We can factorize this one, we can write d plus of 1 into d square minus of 2d plus of 2 equal to 0. You just multiply those two factors, so there arises this cubic equation, d cube minus of d square plus of 2 equal to 0. This is 100% right. And we will equate this d plus of 1 equal to 0 and this factor equal to 0. I can write either d plus of 1 equal to 0 or this factor d square minus of 2d plus of 2 equal to 0. So implies this is d is equal to 1. From this factor, this is d is equal to minus 1. From this is the quadratic, d square minus 2d plus of 2 equal to 0. You can use pen and a paper and solve this quadratic equation by using quadratic formula minus b plus minus under root of b square minus 4ac whole divided by 2a. This is elementary. And we can omit that calculation. You can find the two roots of this d of the form, this is 1 plus minus of iota. That means 1 plus minus of iota. This is a complex roots. So let the one value of d is m1 is equal to minus 1. Those are the two values. M2 is equal to 1, I will take positive 1 plus iota, and M3 and M3. This is M3 is equal to, let it be this is M3, I will take 1 minus of iota. Those are the three, this is plus minus, because M1 and M2 and M3 are of the form. First of all we will rub off and I will continue this lecture here from those who are very roots of this quadratic, and this is here real root. Fine, again here this is M1 is equal to minus 1 You clearly know that m2 and m3 are of the form, both the roots m2 and m3 are of the form. This is real part and this is imaginary. This is real part and this is imaginary. So m2, I can write m2 and m3 are of the form alpha plus minus of iota beta. Means you know that in front of iota there is 1, in front of iota there is 1. We say that implies m1 is equal to minus 1, m2 and m3 are of the form alpha plus minus of iota beta. Means its real part is here is alpha, here is 1, here clearly you know that alpha is equal to 1, in front of iota here is 1, here is 1 again. We say that alpha is equal to 1, beta is equal to 1. For this you know that whenever you have got any complementary function, it is one of root is real and next two remaining roots is or quadratic or a complex alpha plus minus of iota beta, alpha plus minus of iota beta. Its complementary function is like this. Therefore complementary function is equal to c1 of e raised power m1 of z. Why I take z? Because in that very equation, that is auxiliary equation, that is represented, so that given equation, that is the complement linear differential equation with constant coefficient, is converted in terms of z. That's why I use here the variable z. So this is c1 of e raised power m1 of z plus of c2 of cos of beta of x, plus this is, we can write e raised power alpha of x. Sorry, this is e raised power of alpha of z, c1 of cos of beta of z plus c2 of sin of beta of z. We can insert all such values, the value of m1 and alpha beta we can insert here. The resulting complementary function is like this. Complementary function is equal to c1 of e raised power m1 is minus of z plus e raised power alpha is 1 into z is z, c1 of cos of beta. What is beta here? Beta is 1. This is 1 into z is z plus c3 of sin of beta is here z again. This is 1 into z is z, beta is 1. So this is the resulting complementary function for the given differential equation, which is linear differential equation with constant coefficient. But our result is not linear differential equation with constant coefficients, but the given differential equation is a Cauchy's homogeneous linear differential equation with variable coefficients. That the variable there is x. That means our complementary function must contain the variable in terms of x. In terms of x. So we can transform this complementary function. You know that this is c1 of, the transformation was, look it here. This is z is equal to we have put it x is equal to e raised power of z, or the value of z is equal to log of x. When you will see in complementary function z, you can use log of x. You can use log. Whenever you see e raised power of z, I will take here e raised power of z. You can use the transformation. You can use x. When you see z is z there, you can use log of x. I will use both the concepts here. So c1. This is we can write 1 divided by this is here 1 divided by e raised power of z. I can use one more step here, plus of this is e raised power z as it is. This is c1 of cos of z. I will write again c3 of sin of z. Sin of z. Here we can write again this stuff. This is complementary function is equal to, this is c1 arbitrary constant e raised power z. What is e raised power z here? This is here x plus times of, this is, what is e raised power z here? Again x. This is c1 of cos of, what is z, value of z? You can see here z is equal to log of x. You can use, as per the value of z is concerned, you can use log of x. This is log of x here plus c3, this is sine here. You can use again log of x here. So this is clear. What we can say, this is the required complementary function for this question. This is required complementary function. So there is a beautiful concept. That means we have given ours differential equation, given differential equation, that was a Cauchy's homogeneous linear differential equation that contains a variable x. The resulted differential equation was, this given differential equation was transformed into a resulted differential equation that is termed in terms of z. We get a complementary function, complementary in terms of z. We transform again that complementary function into a variable x. That means that is the required complementary function for the given differential equation, that is c1 of, divided by x plus of x into c1 of cos of log of x plus c2 of sin of log of x. This is one more I can say. Now the second thing is the particular integral. That means particular, we must find the particular integral, then sum up with the complementary function. To find the complementary function for this, see we have written this one here, and now we will move on for particular integral. This is here now. My method, this is particular integral, we can write here 1 divided by auxiliary polynomial. Multiplication of right hand side. As we have already done for this, 1 divided by auxiliary polynomial. Why is auxiliary polynomial? You know that. When you will, the coefficient of y is here, underline this d cube minus d square plus up 2. When you equate to equal to 0, this becomes an auxiliary equation. When you will take this one without equating something, so this is a polynomial, this is known as an auxiliary polynomial. You will paste here this one, this is d cube minus d square plus of 2 is as it is. We know that this is auxiliary polynomial. Multiplication of right hand side. What is the right hand side of the given differential equation? This is the differential equation. What is this differential equation? This is a differential equation which is a linear differential equation containing constant coefficients. So its right hand side is this one. You can take this right hand side here. This is 10 times of e raised power of z. This is e raised power of z 10 times. This is 10 times e raised power z plus of e raised power of minus of z. We can use the rules here. We can write 10 here. This is a constant. Multiplication of 1 divided by. We can distribute this one. This to this. This is distributive law. This is the quantity. We distribute it in both here. I can write again. This is here 10. I will show in braces. This is e raised power of z. I can write 1 divided by d cube minus of d square plus of 2. This is e raised power of z. Plus is here. Plus, I can write again this one. This is 1 divided by d square, d cube minus of d square plus of 2. This is e raised power of minus of z. You know that, you know betterly the rules of this whenever you see exponential function. For the value of d, you can write the coefficient of z here. Coefficient of z, what is in front of z? Here is 1. So you can use d is equal to 1 in this term. You see, you can use, you just putting the value of d is equal to 1. Rule says in front of z the value is 1, you can use d is equal to 1. If there is 2, you can use d is equal to 2. If here is in front of z minus 1, you can use d is equal to minus 1. Same rule for this. So this is an exponential function. In front of z there is minus. That means it is not minus only, it is minus 1. So we can use d is equal to minus 1 and insert it here. So it will come to be equal to, let us take the value of d is equal to 1 here. So 1 divided by, this is d, we can write 1, this cube minus of, this is 1 square minus 2 plus 2. This is e raised power of z is as it is plus times of. This is 1 divided by. This, we can insert minus 1 here, minus 1 cube minus of minus 1 square. This is plus of 2. E raised power minus z is as it is. We can write. I will rub up here and continue this practice again. Times of this particular integral, I can write here particular integral is equal to, this is 10 times of, this is 1 divided by 1 cube is 1, 1 minus 1 is 0, here remains only 1 by 2. This is e raised power of z. It is calculated here. I can write plus here. This is 1 divided by, this is 1 divided by, minus 1 cube is minus 1. This is minus 1 square is plus 1 plus 1. I can write here, this is again minus 1, this minus is as it is, this minus 1 square is positive 1, I can write here, plus minus is minus, this is plus 2. This is beauty here, I can say minus 1 and plus 2, this will tend to infinity, only this term tends to infinity. This is here case of failure, case of failure, this is case of failure. Whenever you see case of failure, so you must differentiate with respect to d only denominator, because denominator tends to 0. Denominator tends to 0. This whole term tends to infinity. This whole term tends to infinity. I must differentiate this idea. So this idea, this one I must differentiate. Before putting the value d is equal to minus 1, that very line I must differentiate. Only that term which tends to infinity I must differentiate with respect to d. So I will write here again particular integral is equal to, this 10 is continue. This first term I can write as it is, this is true here, 1 divided by 2 e raised power of z, but the second term has got a fault in the denominator because this tends to 0. That is why we can say this is case of failure, because this term it tends to infinity. Why so? We say this tends to infinity is the case of failure because every particular integral tends to a finite limit. So because this is big for the particular integral never tends to infinity, so we can correct this step here. Before putting the value d is equal to -1, this is the step we differentiate it with respect to d in the denominator. D cube has got differentiation, this is 1 divided by d cube has got differentiation 3d square minus d square has got differentiation with respect to d 2d plus 2 is a constant quantity, its differentiation is 0. You can write e raised power of minus z. So continue the rule here. D is equal to you will insert again d is equal to -1. Rule is same, it will proceed as it is because in front of z there is minus of 1. Here is minus of 1. You can use d is equal to -1. I will rub up here and continue. Let's move here. This is particular integral again is equal to, this is 10 times, this is 100% correct. This is 1 divided by e raised power of z. This is plus times of, whenever I insert the value d is equal to -1. When I insert d is equal to -1 here, if it tends to 0 again, then you will differentiate. You will differentiate with respect to d and add here and multiply the thing in the numerator, the coefficient that we say that the variable here I will insert here because it is a case of failure. I differentiated here. I can use the variable here z. I can use this tells that this z because it is failed single times. When it fails again, when I insert d is equal to -1, when it fails, if it fails again, so we can insert again z. That means that z and this z become a z square. So we can use here, we will continue the game till that the process terminated when this quantity becomes a finite quantity. So I will use d is equal to -1 here. Z is as it is whole divided by, this is 3, and as the value of d is here, we can write -1 and this is square. This is, I can write, this is minus, this is 2. As per the value of d is concerned, we can write -1. This is e raised power of minus of z, is as it is. Let's take here, this is 10 times of 1 divided by 2 e raised power of z plus of, this is z times of 4 divided by 3 is as it is. -1 square is 1, this is minus 2 into minus is plus here, 2 ones are 2. This is here e raised power of minus of z. We can write here, this is 10 times of, this is 1 divided by 2 e raised power of z plus z divided by 2 plus 3 is 5 here e raised power of minus of z. I can multiply this 10 here. This becomes, I will repeat, I will continue the game here. This is 10 times, I will multiply, this is 10 divided by 2 into e raised power of z plus this is 10 times of, this is 10 times of z divided by 5 into e raised power minus of z. This is 2 ones are 2 5s are, this is 5 ones are 5 2s are. So it will come, this is 5 here, this is 5 here, this is e raised power of z, this is plus, this is twice times of z into e raised power of minus of z. So that is, this is the particular integral. This is the particular integral for this question. It contains the variable z, but our given differential equation, which is a Cauchy's homogeneous linear differential equation with variable coefficients, it contains variable x. That means I must convert again particular integral in terms of x. So we can again write particular integral is equal to 5 times of e raised power of z. What is that? E raised power z? E raised power z is x. So we can write, as per e raised power z is concerned, we can write x plus twice times of, what is the value of z here? Z is equal to log of x. That is, we can write log of x. This is log of x. This is e raised power of z. I can write again, this is e raised power, I can take in the denominator, it becomes 1 divided by e raised power of z, but e raised power z is x. So in the denominator I can write, this is this one. This is the particular integral, required particular integral for the given first differential equation, given differential equation. So I combine this particular integral with the complementary function, given complementary function. So we can require a complete solution. Thus the complete solution, thus the complete solution of first given differential equation is as y is equal to complementary function plus particular integral. What is complementary function for this one? Complementary function, this one. I will take here this right hand side and paste here. This is c1 divided by x plus of x into c1 of cos of log of x plus c2 of sine of log of x. This is complementary function plus particular integral. I will take particular integral this right hand side here. This is 5x plus 2 times of log of x divided by x. So this is the required solution for the given generalized, I say take a numerical here, Cauchy's homogeneous linear differential equation containing with variable coefficients. I first of all transform by putting the values inside this Cauchy's homogeneous linear differential equation, transform it into a linear differential equation with containing constant coefficients. Variable coefficients is converted into constant coefficients, and solved that very with linear differential equation with variable coefficients, and finding the solution by taking y is equal to complementary function plus particular integral, finding complementary function and particular integral first, and converting in terms of that was we find that those values complementary function and particular in terms of z, and converted in terms of x, and used that y is equal to complementary function plus particular integral, both added here. So this is the required solution. Our viewers are at international level, so brevity is the soul of it. Thank you very much.